All right, good. So today we're going to start an altogether new topic in our condensed matter course. And in the previous 10 lectures, we've seen how we describe the crystalline structure. Starting from the lattice, we populate the lattice points with the bases, and the crystal structure emerges. And the crystal structure has a certain symmetry, which is described by the 230 space groups. So we tried to understand the international crystallography tables, the standard tables, and then we also invoked the concept of the reciprocal lattice, which is just the Fourier transform of the direct lattice. And we recast the problem of X-ray diffraction into the Fourier space. And we understood the Bragg's law, which states that the change in the wave vector of an incident X-ray must equal a reciprocal lattice vector if an X-ray diffraction peak is to be observed. The Bragg's law gave us the allowed directions for the scattered X-rays. And finally, we tried to deduce the intensities of those X-rays by introducing the concept of the structure factor, which also comes out from Fourier theory. And we observed that in certain Bravais lattice types, for example, FCC, BCC, certain planes never reflect, and they lead to what are called systematic absences in the diffraction pattern. Homework number 4 is a comprehensive homework, which is due by the end of this week. So I hope you do have some time to start early. Today's lecture is going to be on a different note. Let me share my screen. All right, and what I'm trying to do today is lecture number 11, and I'm going to talk about quantized free electrons inside crystals. And the kind of crystals that I'm going to mostly talk about and for which this model is mostly valid are what are called metals, which have been known to mankind for thousands of years now. Right, so let's get started. Now consider some metals and just consider the conduction electrons. And these are the electrons that are in the outer shell of the atom. For example, sodium, which has 11 electrons. It has an electronic configuration 1s2, 2s2, 2p6, 3s1. So if you look at this 3s1 electron, it's a single electron. It's in the valence orbital, the outer shell. This electron can get out from the atom. The atom will be ionized. A positively charged core will remain. A certain electric potential will exist around that core. And you know very well from your electricity and magnetism that if I were to plot this electric potential versus the distance from the center of the nucleus, the potential is going to look like a Mexican hat. This is my curve for the potential, the electric potential near a positively charged nucleus. So it's just like a hydrogen atom, though the effective number of electrons is not 1 in this case. Uh, and, and the electron, which has now become free, which has been stripped out from the atom, is now ready to roam about in the entire expanse of the crystal. So we get a sea of electrons, and these electrons see these potentials which exist at the fixed sites of the positively charged cores, and the separation between these ions is A. For example, A is the lattice spacing. So the electrons now see this corrugation, this periodic arrangement of potentials. Okay, If I were to model these potentials by Dirac delta, uh, the Dirac delta function, I would get a potential of this form. Some V naught. All right. So now the electrons, which are our focus of attention in this lecture, they are free. They are ready to go around and roam about inside the sea that we have created of all of them. So this is called the sea of electrons, or the conduction sea. Now what we're trying to do today, if we do not invoke quantum mechanics, we get what is called the Drude model. Now, the Drude model is a 19th century model, but it's extremely powerful. And you must have seen this model already in modern physics, perhaps in statistical mechanics, in which this sea of electrons is modeled as a gas, an ideal gas of electrons. And then you use classical kinetic theory of gases to model the distribution, the energy distribution, the speed distribution of these electrons. You get the average energies and so on. But now what we're going to do today is, I'm not belittling the importance of the Drude model. It's a model that gives, to a first approximation, excellent results. But this is something that you can look up on your own, or revise your notes from previous lectures. What I'm going to do today is I'm going to bring in quantum mechanics. So I'm going to look at the quantized theory of the free electron. And we all know that when we talk about an electron, and by the way, the electron, so now we have many electrons. If we have n atoms inside a crystal, say n sodium atoms, each electron is donating, each atom is donating one free electron to the electron C. So we have n free electrons. The electrons, as you know, are positively negatively charged particles. They're going to interact with one another. We ignore this interaction between electrons. We just assume that electrons are so far apart that they hardly make any interaction with one another. And we also ignore for the time being the corrugated potential, the contoured potential that I've drawn over here. We just ignore this. We say that the potential is constant, and all the electrons, one, they are independent of one another, they're non-interacting. Second assumption is that they are in a constant potential. Let's call that potential V, just V or V naught. So if you were to model these electrons, the potential profile for a solid of this kind, if the solid has a length L, just look at one dimension of the solid, the potential is just constant along this length. Okay, and the electrons are inside this potential well, so to say. And all of the electrons see the same potential, they see a mean potential, and they're non-interacting with one another. Now we would like to use the power and the glory of quantum mechanics to describe these non-interacting electrons in a uniform potential. And how do we describe the behavior of an electron? What kind of equation would we require to describe the electron here? What's the equation of motion for such an electron? By the way, there are n electrons, and since each electron is independent and it's non-interacting with another, we can just focus our attention on a single electron. And all the electrons will have the same wave function that they satisfy and the same solutions to the wave function. So what kind of equation do we need here to describe this electron? Anyone? What physics do we bring in here? What's the equation of motion? Do you use Newton's law, F equals ma? How do we describe, if we knew a little bit of quantum mechanics, how would we describe this electron? What equation would we use?
Schrodinger's wave equation.
Schrodinger's wave equation, which goes as minus h bar square 2 over m partial square, and I'm just looking at the time independent form, plus v naught psi x equals E psi x, where E is the energy of the electron. and V naught is the constant potential. Now, if this potential is constant, psi is the wave function. And here I'm focusing my attention for the time being on a one-dimensional solid or a nanowire. And then I can simply lift and boost this idea to 3 dimensions. That's not a big problem, but it's easier to understand the one-dimensional toy models before we go ahead. So this is the time-independent Schrodinger equation, as you all know. Something which should be at the back of your mind always. So when you wake up in the morning and someone asks you, mother asks you, what is the time-independent Schrodinger equation, you should be able to tell at the back of your palm that this is the time-independent Schrodinger equation. This is how a physicist should know this, like the back of his hand. All right, so any confusions about this equation, or I can just move on? All right, so this potential here is a constant. So the idea of a potential is just to set out a reference for the energy. So I could take this V naught, for example, to the right hand side, and I'll get E naught minus V. And that is just going to shift the effective energy. So I might as well take this potential to be equal to 0. So without loss of generality, this is going to be true. So now my modified Schrodinger equation, my simplified Schrodinger equation looks like this. All right, so how do we solve this equation? What is the solution to this equation? These functions, what are they called? They are called wave functions. And these wave functions are solutions to the Schrodinger equation, and they describe the electron. They describe all the properties of the electron. When we take the modulus square, it describes where the electron is, where is the highest likelihood of finding the electron. So what is a solution to this equation? How do we solve this equation, and what does the solution come out to be? क्या होगा इसका solution?
Sir, कोई coefficient multiplied by exponent raised to the power iota into sir, factor
some
k.
All right. So k is some wave number, and we can actually find out what k is. So this is an ansatz, or this is a trial solution. We can insert it into the equation. Let's see what we get. If we take the derivative of this, we get ik psi. If we take the derivative again, we get minus k squared psi. Okay, so now we put this back into our equation of interest, minus h bar square over 2m minus k square psi x equals E psi x. So which means that my energy for the electron is h bar square k square over 2m. And this energy is depending upon the number k. And k must have dimensions of momentum. So k is some object, some number living in the reciprocal space. And we've belabored the concept of the reciprocal space. It's the inverse space, or the Fourier analog, or the conjugate variable to the direct space. So if we have x on one hand, its conjugate variable is going to be a or b. So these are called conjugate variables in quantum mechanics. So the energy of this electron will depend upon the value of k. Okay, let's talk about the momentum. So if I were to take my wave function psi x and have the momentum operator act on it, which is minus iota h bar, partial derivative with respect to x. And we already know that the ansatz, the trial solution that we have, this one, is indeed valid. It is a solution, and it yields the energy each h bar square k square over 2m. So with this ansatz now, which is no longer an ansatz, but is a verified solution, if we were to find out the action of the momentum operator on this wave function, this is simply going to give me minus iota h bar a I k e I k x, which is h bar k psi x. Now this comes out to be an eigenvalue equation, and h bar k's are the eigenvalues, and they correspond to the momentum. So the momentum operator has eigenvalues which are called momentum. So the momentum is h bar k. The energy we've determined is h bar square k square over 2m, and I would like to write small k's with this if I want. So now I have the energy of the electron and I have the momentum of the electron. But the solution is also telling us that this electron and all the electrons inside the solid, they are acting as traveling waves. Okay, so the electron inside the solid is now being modeled as a wave. Okay, and these waves can also diffract just like X-rays, and that's where the concept of the bands comes out. When these waves interfere, certain certain superpositions don't exist, and they'll lead to band gaps, and we'll learn about this. But now we've modeled the electron inside a solid as a wave. So we have a wave solution, and we also come up with the momentum for the wave and with the energy for a wave. And this is just Schrodinger equation applied to a free particle living inside a constant uniform potential. Okay, now if you would like to extend this to 3 dimensions, electron inside a metal is acting like a wave. That's the key. Okay, this wave can scatter, this wave can undergo tunneling, this wave can interfere with other things, and so on. So the electron, the concept of the electron, which is traditionally a particle concept, fizzles out and becomes slightly ghost-like and becomes a wave. Okay. Now, if I were to extend this to 3 dimensions, instead of x, I have a wave function that is now dependent upon r. I need to write a constant, some constant which I can determine, ei k dotted with r. Now, since I have this k value here, this value of k here, which is the momentum itself of the wave, I can put a small subscript with this psi. It doesn't harm me, it just doesn't do anything. Now, this normalization constant can also be determined from the idea of normalization. And normalization means that the electron wave must exist inside the solid. So if I have a cubic solid, now I'm not talking about the crystalline structure, I am talking about a piece of solid that is in the shape of a cube. Each length is L. Then this A I can determine from normalization, which we know that take the modulus square of psi and then integrate over the entire volume. I can determine what A is. This turns out to be 1 over square root of the volume. Okay. I hope you can do this on your own. You just need to integrate over all of space psi k and set this equal to 1. Okay. And your space is now the volume of this solid. Okay. V. So this is the the solution to the Schrodinger equation for an electron inside a solid, assuming that it is a free particle in a constant uniform potential. All right, now we need to take a closer look at K. Just looking at the exponent factor here, K is conjugate with R. So anything that is in the exponent must be dimensionless. So K must have dimensions of 1 over distance. And this is the property of the reciprocal space, as you all know. Now, but let's take a closer look at K and impose certain boundary conditions on K. And those boundary conditions, there's a well-known rule in quantum mechanics that confinement leads to quantization. Now, what this means that if I have an electron roaming about in space and it is not constrained spatially to remain in a certain region, it can have any value of k. Its momentum, its wave function could be its wave number, and its wavelength could be anything. But once you restrain the electron to remain within a certain volume or on a certain length, the value of k becomes quantized. You all know this very well when you study the particle in a well. So what's the particle in a well? If I have a well of length L, we know that k is going to be uh, quantized. So this is going to be quantized, and this will only be true when L holds an integral number of wavelengths. Okay, so this lambda equals 2L over n, and k has to be equal to 2 pi over lambda. So lambda is 2L over n. So k is quantized in units of pi over L. So k could be 0, it could be plus pi over L, minus pi over L, plus 2 pi over L, minus 2 pi over L, and so on. So this is what we learn from the idea of a particle in a well. And since the energy is quantized in this fashion here, k is quantized, the energy becomes quantized. And the energy becomes quantized as E k h bar square 2n. K square is now n square pi square L square. So Ek is now quantized by this, what has emerged as a quantum number for a particle in a well. And if we were to plot the energy manifold, the energy is going to be quantized. En0 and 1 gives a certain energy, and 2 gives a certain energy, and 3 gives a certain energy, and 0 really means that the particle doesn't exist. So the energy becomes quantized because of quantization and confinement. And confinement assumes that at these boundaries, the wave function must go to 0. Now we can use exactly the same concept in solids. We have an electron inside a three-dimensional solid, and the electron, of course, cannot hop out of the solid unless you heat it up or there's some kind of thermionic emission. But generally, the electron is confined inside the solid. Now, if I were to talk of a one-dimensional solid of length L, so this is my X, this is the length of the object, L, and the solid might comprise of atoms inside this, and many atoms. So if this separation is between atoms is small a, which is lattice constant, which is of the order of nanometers or angstroms, and L is 1 millimeter or something of this kind, even then there is a huge number of atoms inside this one-dimensional solid. Okay, so what I've drawn here is unrepresentative. It just illustrates the concept. So now if I have a situation of this kind, I can impose certain boundary conditions, and I could impose that the value of the wave function at some x is the same as the wave function at x plus L, which means that at the boundaries of this solid, the wave function is the same. Okay, so this kind of boundary condition is called a periodic boundary condition. Now, in this boundary condition, we just use this boundary condition. Now, we know that the wave function here is going to be EI let's take 2 points. Let's take x equals 0 and x equals L. So at x0 equals 0, I have E I k dot 0, which is A. But this must be the same as the wave function at x equals L. And at x equals L, I have E I k dot L, which must also equal A. So this means that my E I k L must equal 1. By the way, there's no need for a dot here because it's just one dimension. So just look at this, what I've underlined. K must be such that E raised per I k L equals 1. Okay. Now this, when will this be true? This will be true when K is some multiple of 2 pi. Let's denote this by n. Some multiple of 2 pi over L. Sorry. When this is true, this means that my K has now become quantized. So my K can take up value 0 plus minus 2 pi over L plus minus 2 into 2 pi over L and so on. Now 2 pi over L and these terms give us a hint that K is not a reciprocal lattice vector. It does not represent a reciprocal lattice, but it's some vector in the reciprocal space. And we have to differentiate it from the reciprocal lattice vector, because the reciprocal lattice vectors, although they have the same dimensions, they are of the form H A star plus K B star plus E C star L C star. The A star, of course, can have a length 2 pi over A, etc. But it's 2 pi over A, where A is the unit cell size, and here L is the size of the solid. Okay, so just keep that thing in mind. So the values of K become quantized because of the periodic boundary conditions. Any questions? So if the value of V of K becomes quantized, so let me draw this on a, let me draw the K space. Now K can be 0, K can be 2 pi over L, 2 into 2 pi over L, 3 into 2 pi over L. Likewise, we can go to the other side. Only values of K that lie on these tick marks, they are allowed. And K gets quantized. And if you were to talk about a reciprocal lattice vector in one dimension, the reciprocal lattice vector, say, if the unit cell spacing is A in one dimension, then the reciprocal lattice vector will have a length 2 pi over A. And 2 pi over A could be a big vector, a big vector here. Because A is much smaller than L. And one reciprocal lattice vector can fit in trillions and trillions and trillions of K space points. So both the reciprocal lattice vector and the K points live in the reciprocal space, but the concept is slightly different. Okay, so just keep this thing in mind. But both of them live in the K space of the reciprocal space. Now, if you were to extend this concept to 3 dimensions, by the way, the energy is now quantized since I can define a quantum number n here. This is the quantum number, new quantum number that has arisen. This quantum number n appears in the energy. So h bar square over 2m, k square is now n square 4 pi square over L. Okay, this is k square. So my energy now becomes quantized, and I can characterize the energy by this quantum number n. And the quantum number n is basically, it is called the spatial or the orbital quantum number, because it is dealing with waves in space. Okay. And the momentum also gets quantized. And the wave function itself in 3 dimensions can now be written as 1 over under root v ei k dot r. Now this k is quantized. And how is it quantized? if I'm in 3 dimensions, then I can have an energy. Now in 3 dimensions, this energy is going to be n square is going to be nx square plus y square plus nz square, where nx is the quantum number for quantization along x, ny is the quantum number for quantization along y, nz is the quantum number for quantization along z. So if I were to plot these points in a 2-dimensional plane, so I have a kx axis and I have a ky axis. So the allowed values of k along one axis, I've already determined them what they are. They are separated by 2 pi over L. It's a cubic solid. Cubic means cubic shape. Likewise, along the y dimension, ky, I have a spacing 2 pi over L, and I have all of these points. So this is a picture of the wave in k space, or a picture of the electron in k space, in the Fourier space. Okay, and it's so the k is quantized. So kx is quantized along x, k is quantized along y, and k is also quantized along z. And the total k, which is of course a vector, and its magnitude is going to be kx square plus ky square plus kz square, and this is going to be n square 4 pi square over L square, where n square is the expression over here. So the energy also becomes quantized. So if in 3 dimensions, if you're in 3 dimensions, and we have a volume of a solid which is L cube, what is, so if I'm in 3 dimensions, I would have a 3-dimensional grid. So let me try to draw this grid in perspective. So let me make an attempt of drawing these points in perspective. So this is the kind of grid that I will construct, a 3-dimensional grid of points in K space. This is also the reciprocal space, but the reciprocal lattice vectors, they are much bigger. So one reciprocal lattice vector will subsume many of these small K points. Now, my question is, if the volume of the solid is L cube, what would be the volume of one small cube, the smallest cube in K space?
2
So
pi
you
over
can
L whole ka cube.
Right? So the volume in K space is going to be 2 pi cube divided by the volume in the direct space. Okay, so there is a reciprocal relationship between the size of the solid and a size of a small K point or a K cube in the K space. Okay, and by the way, there is also this concept of degeneracy. There will be multiple K points. So if an electron has a certain wave number, it exists on we say that it exists on a certain k point. Okay, the k value tells us the energy of the electron. The k value tells us the momentum of the electron. We know that the energy of the electron is going to be equal to n square uh, n square h bar square, sorry, excuse me, h bar square over 2m n square 2 pi over l square. So the energy is quantized. And of course, you can always shuffle between k and n. They are both related. They both represent quantization. They're just off by a scaling factor. Now this n is depends upon nx, ny, and nz. So different values of nx, ny, and nz can give rise to the same energy. So if I make a table for nx, ny, nz, and here I mention en, and I just consider h bar square over 2m 2 pi over l square, which means I just consider the value of n square. Okay, then I can have 0 0 0 here, which gives me an energy 0. I could have 0 0 1 here, which gives me an energy 1 square, which is 1. But minus 1 would also give me the same energy. But this would also give me the same energy. This would also give me the same energy. So all 6 of these combinations of n's give rise to the same energy. Okay, so the state of the electron is defined by the value of the 3 quantum numbers nx, ny, and nz. So if I would like to write this wave function inside a ket, this is the state of the electron. It's totally defined by nx, ny, and nz. By the way, I'm ignoring the spin of the electron. That is another degree of freedom, but I'm ignoring that. I'm only looking at the spatial degrees of freedom, also called the orbital degrees of freedom. So all 6 of these values of the quantum numbers give rise to the same energy. Okay, so this energy is 6-fold degenerate. Okay, energy 0 is non-degenerate. Likewise, I can have this scenario, sorry. Now these 12 different kinds of states. So this is 12-fold degenerate. This is 6-fold degenerate. This is non-degenerate. These 12 different kinds of and combinations of nx, ny, and nz give rise to the same energy. Okay, so this is the concept of degeneracy. And if I would like to make this into an energy level diagram, I have an energy level proportional to 0, I have an energy level proportional to 1, and there are 6 kinds of these states. And then I have a 12-fold with an energy of 2. Okay, 2 units. तो 3 4 5 6 7 8 9 10 11 12. So I can make this energy level manifold. Okay, and I get degenerate states for different values of n. Okay, likewise I can have plus minus 1 plus minus 1 plus minus 1. This is an 8-fold degenerate state, an energy of 3 units. Yes, Heather.
सर इस तरह हम जीमान इफेक्ट स्टडी करते हैं, उसके अंदर हम कोई मैग्नेटिक फील्ड लगा लेते हैं और ये सेपरेट हो जाती हैं डिफरेंट फोल्ड्स ऑफ सेम एनर्जी स्टेट. तो इसमें पॉसिबिलिटी है कि हम लोग किसी पर्टिकुलर डायरेक्शन के अंदर अगर मैग्नेटिक फील्ड लगाते हैं तो सारी स्टेट सेपरेट हो जाए.
So we need something that responds to a magnetic field, and that something is called the spin. So far I have neglected the spin, but really each one of these levels, each level here is yet 2-fold degenerate. because of the two possibilities of the spins. So I have a spin up or a spin down. Okay. So when I say 12-fold degenerate, if I include the spin, it's 24-fold degenerate. So these are two spin levels, spin energies, which are exactly one on top of another. So each one of them has a two-fold degeneracy. Each one of them has a two-fold degeneracy. And what the Zeeman effect would do, if I were to apply a magnetic field, these two levels will split up. Okay, like this. Okay, this is what the Zeeman effect does. So each level which takes into account the spatial quantum numbers has a further two-fold degeneracy because of spin. So each level has two possible states. And when we are filling electrons into these energy levels, now how do electrons fill into these energy levels? Energy is going up here. That is determined by the temperature. If the temperature is small, the lower energy levels are filled. But the Pauli exclusion principle says that each level cannot be occupied by more than two electrons. So if you have the third electron, it must go to a higher spatial energy level. Even though the energy is higher, it goes to the higher level because of this degeneracy pressure. You cannot have, because of the pressure imposed by the Pauli exclusion principle. So these electrons inside a solid, they take higher and higher and higher and higher energy levels because of the Pauli exclusion principle. So these are really polysolids or polyelectronic solids that we're talking about here. And we look at more examples of this kind when we talk about the Fermi energy today. Yes, Heather.
Sir, if we do not consider spin, so isn't it possible to differentiate n x is equal to 1 and n y is equal to 1 when it comes to if their energies in any way?
So you have to break the symmetry. Currently, nx, ny, and nz, they are totally the same. There is no distinction between x, y, and z. That is why you cannot separate them. So you have to apply an electric field or a magnetic field. So a magnetic field will lift the spin degeneracy. It breaks the time reversal symmetry. If I were to break the inversion symmetry somehow, say for example with the help of an electric field, I can lift this degeneracy. Because the electric field is pointing in a certain direction, it's breaking the uniqueness of space. If the electric field is pointing along x, and x is different from ny and nz. Okay. And this is what happens in the Hall effect, which is a really important effect. And the Hall effect has, by the way, given rise to many Nobel Prizes in physics, the quantum analogs of it. Okay, topological insulators are based upon quantum spin Hall effect. So you can break the degeneracy of these levels by breaking the inversion symmetry. Okay, so you have to break the uniqueness of space so that nx is different from ny and nz. Okay, did I answer your question, Heather?
Yes, sir. Thank you.
All right, now I would like to come up with the concept of the Fermi energy. And the Fermi mansion itself, which has the energy, it has the Fermi sphere, has the Fermi volume, Fermi wave vector, so on. So the entire Fermi edifice, the entire enterprise of Fermi. Enrico Fermi, by the way, was one of those rare physicists who was a top class experimental physicist and theoretical physicist at the same time. So Italians are always like that. So, so any questions after this point? Let's take a half a minute break while I get some water for myself. G, any questions? All right, so now we have these. Let me arbitrarily draw these levels corresponding to various values of K arbitrarily on energy diagram. My energy is going up here, and I have these levels of K. The energy is quantized in units of n square, h bar square over 2m over this is 2 pi over L whole square, okay? And if in terms of K, I have h bar square K square over 2m. And this K is quantized. So now I've mentioned that each level can be occupied by a maximum of 2 electrons. So the electrons can go into these levels. Now the number of electrons is fixed. If, for example, I'm talking about monovalent atoms like sodium, sodium has 11 electrons, and the C of electron is formed by the donation of only one electron from a sodium atom. So depending upon the size of the solid and the number of moles present inside the solid, I can determine how many free electrons exist. So n is fixed, and n is fixed by the volume of the solid. So n is fixed means that Zn electrons exist inside the conduction band or inside the Fermi C, as it is called. Z is the valence of the electron of the atom. Okay, so now these electrons have to rise up the ladder. Each level is filled by 2 electrons, and the other next goes to the higher level. So the energy is going up, 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 and up because of the Pauli exclusion principle simply. Excuse me. Excuse me. Can you see my screen?
No sir, अभी नजर नहीं
नहीं
आ रही.
सर
Just okay. Because of the Pauli exclusion principle. Now there's a maximum value of K that is allowed. Okay. So now the discussion that we have so far is at precisely at 0 Kelvin. So all the discussion that I'm going to have today is at 0 Kelvin. Now at 0 Kelvin, the solid can have a maximum value of K because the electrons just keep on filling, and when all the electrons are exhausted, they reach a certain value of K. That K is called the Fermi wave vector, Kf. Now if I'm in 3 dimensions, so now I'm going to focus my attention on three dimensions, and I'm going to look at the K space only. So I can either look at things in the real space, the direct space, or the K space. It doesn't matter. Both of them are equivalent representations. So I have Kx here, I have Ky here, and I have Kz here, and I have points, the K points, because K is quantized. And then I have third dimension as well. So I have a grid or a network of points, okay, in 3 dimensions. And a maximum value of K is allowed. So I can draw a sphere inside K space, and I can say that all the levels inside this sphere, they are filled. So inside the sphere I have all the levels filled, and outside the sphere all the levels are empty. Okay. Now remember that these k points are really fine together. They, because the separation between these points is 2 pi over L on each dimension. L is large. Even if L was, if L were 1 millimeter, 2 pi over L is going to give me some number, and you just compare it with, you can find out that there'll be large, these points are really small, close together as compared to the reciprocal lattice vectors. So what does this have to do with the reciprocal lattice vector? I'll explain later. But you have this grid of k points, okay, and k values up to a certain level they are filled. This sphere that I've drawn is called the Fermi sphere. Excuse me. Please give me a second. I'll just change the batteries here. कोई सवाल इतनी देर में पूछना है आपने?
आपने कहा था कि जीरो केल्विन पे हम कंसीडर कर रहे हैं, लेकिन अगर टेम्परेचर ज्यादा हो तब भी तो के के लिए लिमिट होनी चाहिए ना, नंबर ऑफ इलेक्ट्रॉन्स तो लिमिटेड ही हैं, तो उस केस में क्यों नहीं लेते?
हाँ, लेकिन वो उस केस में कुछ और होगा, वो मैं बताऊंगा क्या होगा. ठीक है, नंबर ऑफ इलेक्ट्रॉन्स तो हर केस में लिमिटेड ही हैं. नंबर ऑफ इलेक्ट्रॉन्स तो नहीं कम हो रहे या ज्यादा हो रहे, लेकिन व्हाट काइंड ऑफ दे, those electrons will go out of the Fermi sphere. Okay, so Fermi sphere is that boundary, that interface, the Mohovic boundary between the filled and the empty k points. Okay, at zero
तो सर
Kelvin,
फिर
that is defined as the Fermi sphere.
तो हम लोग फिर जो फर्मी स्फीयर है इसको हम एज अ फंक्शन ऑफ टेम्परेचर क्यों नहीं लिखते? क्योंकि पर्टिकुलर टेम्परेचर के ऊपर भी तो लिमिट होगी ना कोई,
लेंगे,
क्योंकि इन
यही
लेंगे।
मैं ये खाकसार यही काम करेगा कि वो इस फर्मी एनर्जी को बताएगा कि क्या टेम्परेचर पे डिपेंडेंस है, और आप देखेंगे कि टेम्परेचर पे बहुत वीक डिपेंडेंस है. ठीक है. So now this Fermi sphere is going to have a certain radius, and that radius is defined to be kf. Okay, so the volume of this Fermi sphere is 4 over 3 pi kf cube. Now what I'm trying to do, I'm trying to find out the energy of the Fermi electrons. The electrons that are at the Fermi sphere, what energy do they have? Okay, that's what I'm trying to do now. So the volume of this Fermi sphere is 4 over 3 pi kf cube. And what is the volume of each k point? It's 2 pi cube over v, correct? So the number of k points inside this Fermi sphere is the expression that I've written over here. Got it? ये बात समझ आई?
Yes, sir.
All right. Now, on each k point, so each k volume, small k volume, each cube in the k point can accommodate 2 electrons, right? Because of spin degeneracy. So the number of states that I can have, or the number of electrons that I can have inside the k sphere, is given by the expression that I've written over here. This factor of 2 arises because of the 2 possible spin states, up and down. And this must equal capital N. Okay. So if I were to just simplify this a little bit, what do I have? 8 over 3, 1 over 8, 1 over pi square, kf cube b. Okay. So now the number of electrons and the size of the Fermi sphere, they are interrelated. They should be interrelated, correct? Now, if I were to take V to the other side, I will get the number density of electrons, the number of electrons per unit volume, and this is equal to 1 over 3 kf cube over pi square. Now, this number of density of electrons depends upon the density of the metal. It depends upon the valency of the metal. Okay, that's what, and it depends upon the molarity of the metal, the Avogadro number, and so on. So you can find out the number of electrons per unit volume. This could be a small do-it-yourself problem. Take sodium, look at its density, and find out how many electrons exist per unit volume in the Fermi sea. The electrons that are valence electrons that have been donated to the Fermi sea. So now from this, I can determine what Kf is going to be. Kf is going to be 3 pi square n or 1 over 3. Now this is the Fermi wave vector of the electrons. The maximum wave vector an electron can have at 0 Kelvin. And all the electrons will have wave vectors with magnitude smaller than this Kf. And I can also find the energy corresponding to this Fermi wave vector. And that energy is going to be h bar square over 2m Kf squared, which is h bar square over 2m 3 pi square n 2 over 3. And this is called the Fermi energy. So the Fermi energy is the maximum energy any electron can have at 0 kelvins inside a Fermi sea of electrons inside a metal. This is how we define a Fermi energy. The Fermi energy, by the way, is the chemical potential at 0 Kelvin. Okay, so I'll talk more about this later, but I can define a Fermi wave vector, I can define a Fermi surface, I can define a Fermi energy, I can also define a Fermi temperature. So if I were to equate this EF with KB TF, this TF is a Fermi temperature. So it tells us that if Pauli exclusion principle were incorrect, and still electrons had to go to the Fermi energy, what temperature would be required to achieve that if you were just considering classical thermal system? Okay, and the Fermi energies, if you look at typical values of N inside metals, this Fermi energy could be of the order of thousands of Kelvin. It could be of the order of few electron volts, say 5 electron volts. At room temperature, the energy EKBT is about 25 milli electron volts. So now you have a metal, and even if it were at room temperature, and suppose that the Fermi energy does not change with temperature, the Fermi energies and the Fermi temperatures are much larger than the Fermi temperatures. The Fermi temperatures are much larger than T. So the electrons, in a sense, are extremely hot because of the Pauli exclusion principle. If you were to put a thermometer inside the electrons, you won't be able to measure this temperature because this is not thermal energy. This is the energy that arises because of the Pauli exclusion principle. Sometimes it is called the degeneracy pressure. Okay, and this is the same degeneracy pressure which gives rise to neutron stars and white dwarfs and objects of this kind. So any questions about this? And we'll talk about temperature dependence in a while, so we have to be patient about that. Right now we're just discussing 0 Kelvin scenarios.
सर फर्मी टेम्परेचर की आपने जो बताई थी डेफिनेशन या फिर उसको थोड़ा सा डिस्क्राइब किया तो दोबारा कर सकते हैं? व्हाट इज फर्मी टेम्परेचर?
देखें, आपके पास एक फर्मी एनर्जी है. Any energy can be written dimensional as Boltzmann constant into some temperature. So our definition of the Fermi temperature is the Fermi energy divided by Kb. This is our definition here. And this temperature, if you look at 5 electron volts, which is 5 into 1.6 into 10 power minus 19 joule, and you divide it by 1.38 into 10 power minus 23 joules per Kelvin, which is Kb, you get something of the order of 10 to the power 4 Kelvin. So the Fermi temperature is 10,000 kelvins, even though the solid is at 0 kelvins. This tells us the energy of the electrons is exorbitantly high inside inside the solid, even at 0 kelvins, because there is a huge number of K levels, and each K level can be occupied only by 2 electrons. So the third electron has to hop to a higher energy level, and until all of those energy levels are filled, and the number of levels that need to be filled is determined by the number of free electrons that are available. And the highest electron on the pedestal of this energy manifold, that is on the throne of this energy manifold, is at a really high energy of the order of electron volts. And if you would like to write this in units of temperature, that would be 10,000 kelvins. This is the concept of the Fermi temperature. So it helps us make comparisons with thermal cases. Okay, and you also note here that the Fermi velocity, the Fermi wave vector is proportional to the 1/3 power of the volume density. The Fermi energy is proportional to the 2/3 power of the volume density n. We can also define the Fermi velocity, by the way. So if I were to take momentum, I can define the Fermi momentum. From the energy, I know what the momentum is. The momentum is going to be mvf. This is the momentum can be expressed in terms of the energy 2mef. So the Fermi velocity is defined by 2ef over m. Okay, just from dimensional analysis, you can define all of these terms. And when we look at two-dimensional materials such as graphene, people generally use the term Fermi velocity quite often. And this Fermi velocity could be a fraction of the speed of light. Okay. Now I would like to introduce the concept of the density of states. The most vital concept in all of condensed matter physics, undoubtedly or arguably so, is the density of states. It's really important. It is different for three-dimensional solids, two-dimensional solids. I'll give two-dimensional problems as a homework, but density of states is extremely vital. Let's denote it by GE. Okay. Remember, I'm still at 0 kelvins. So all my discussion so far is valid at 0 Kelvin, strictly valid at 0 Kelvin. It does not depart much, even if the temperature is room temperature, because room temperature is say 300 kelvins, and the Fermi temperatures are 10 to the power 4 kelvins. So even if we are at room temperature, we are very close to the 0 Kelvin scenario. So our discrepancies from the 0 Kelvin assumption are not going to be big. But still, for the sake of puritanistic clarity, I'm going to focus this discussion at 0 kelvins. Gee, there was a question. कोई सवाल? All right, so what is the density of states? The density of states is a concept which is really valid. So if I have an energy surface E and an energy surface that is slightly higher, E plus dE, okay, then the number of electrons in this uh, small area or volume, if this is dn, then I can define dn to be equal to the density of states at the energy E multiplied by the change in the energy dE. So the density of states is a number of states per unit energy. GE is the number of states per unit energy. States, sometimes they're also called modes, a term popular when we talk about quantum field theory in solids, modes per unit energy or states per unit energy. This is the concept of the density of states. And you, all right. So now let me derive the density of states. Suppose I'm still in my K space. Three-dimensional K space. And I have the grid, popular grid that I've always talked about. And now I draw a sphere of radius K, arbitrary radius K. Not Kf, just some radius K. Now the number of points, number of states up to the radius K, starting from 0 to the radius K, is going to be given by the volume of this sphere. Now I don't have Kf, I have K, arbitrary K, divided by 2 pi cube over V to account for the spin. So this turns out to be 1 over 3 pi square K cube V. This is the number of states up to the radius K. Okay. Now let's take the differential of both sides. dn is 1 K cube, sorry, just write V here, V over 3 pi square 3K square. Excuse me, K square, or where am I? Where am I? dn is 1 over 3 pi square 3K square V over pi square K square. This means that my dn over dk is V over pi square K square. I can take V to the other side. dn over dk is chi square over p square, pi square. Now, in order to find out the density of states, GE, I really need dn over de, the number of states per unit energy. But I have dn over dk here, so I can just use chain rule. dn over de is dn over dk over de. So 1 over v, dn over dk is now dn over de. So dn over dk is dn over de, de over dk, k square over pi into dk over de. Okay? So this is what I'm left with. Now I need to find out this thing here. And I'll get GE. So DE I already know is h bar square k square over 2m. So I can immediately determine D. Let's find DE over DK. DE over DK is h bar square over 2m 2k. H bar square k over m. So I just insert this value into this expression. 1 over v dn over de is k square over pi dE over dk is m h bar square k m k pi h bar square. Now let's call this dN over dE is just the density of states. So generally I would like to divide it by the total volume. So I call this thing GE. The density of states is per unit volume. So this is my density of states. I want to express this as a function of E. So I can always do that. So I know that E equals h bar square k square over 2m. So my k equals 2me over h bar. So I just insert this thing into here. My GE becomes m pi h bar square 2m h bar. So I'm left with some constant here, some constant. This is a constant, all of this. Let's call this C. Bingo. The density of states in a three-dimensional solid for free electrons is proportional to the square root of the energy. Okay, so if I were to plot this E and density of states here, I would get a curve of this kind. So as the energy goes up, more and more and more and more and more energy states get clustered together at the same energy. So higher the energy, the degeneracy also goes up. So there are more states at a higher energy E per unit volume as compared to a lower energy. All right. So this is the density of states for free electrons, which are quantized according to quantum mechanical principles in a three-dimensional solid. And the density of states can be measured directly in different experiments, with spectroscopic experiments. They could be measured directly with the most popular technique is scanning tunneling microscopy. STM. and by the way, by looking at the variation of the density of states with energy, you can tell what the dimensionality of the solid is. And this idea has really spurred with the advent of nanotechnology. If I were to look at the two-dimensional solid, such as a layer of graphene or something which is two-dimensional, and the electron, the free electrons are only able to reside in those two dimensions, then this density of states is going to be some constant. It will not depend upon energy. So it's going to be constant, some constant. So this is for two dimensions. And if we were to talk about one dimensions, in 1D, the density of states goes as the reciprocal of the square root. Okay, so this is the density of states in 1D. And if I were to have a zero-dimensional solid, which is called a quantum dot, the density of states is going to be quantized. Dirac delta functions. Just like an atom, one zero-dimensional quantum dot is an artificial atom. Okay, and we know that in an atom, the energy levels are quantized. They come at T sharp values. Okay, so starting from the concept of the Fermi sphere and the Fermi energy, one can determine what the density of states is going to be. Now, in a homework problem, what I'm going to give you is, I would like you to find out the, say, the Fermi energy and its dependence on n for a 2D solid. And I would like you to find out the density of states, 2D solid, and show to me that it is a constant. Now, what you would do is you would draw a two-dimensional say kx is now this axis, ky is here. You would draw the k points in 2 dimensions. You don't worry about the third dimension because the third dimension doesn't really exist. And then what you would do is you would draw not a Fermi sphere but a Fermi circle. Okay, in 2D you have a Fermi circle, and you say that this is kf, and you count the number of modes. So a continuous problem is converted to a mode counting problem. So you count the number of modes inside this circle. You find out the area of each mode, which is going to be 2 pi over L squared. Count the number of modes, take into account the spin degeneracy, find out the Fermi wave vector, and from that find out the Fermi energy, and from that find out the density of states. Okay, and you can prove that this is going to be constant. You can repeat the problem for a one-dimensional solid. Okay, you just lay out your k points on a one-dimensional string. Okay, and count the number of points within a certain length, kf, which is just going to be a certain length inside the one-dimensional k space. One-dimensional solids will have one-dimensional k spaces. Two-dimensional solids will have two-dimensional k spaces. Now, the last thing I would just like to mention is I would just like to write down an equation. What does mode counting means? Mode counting means that if I were to take the density of states, including the spin, I'm now factoring spin into the density of states, and I would like to integrate this from 0 to Fermi energy. This is going to give me the number of states. This is what is meant by mode counting. Okay, so by the way, this is going to be small n. So the density of states integrated from 0 to the maximum energy is going to be give me the total number of states, of course per unit volume, because this is per unit volume. This is what is meant by mode counting. Excuse me. So I'd like to stop here, and in the next lecture I would like to break this assumption of 0 Kelvin, and I would like to look at the thermal properties of these electrons. So as you increase the temperature, what happens to the Fermi energy? That will help me introduce the concept of the chemical potential, which is based upon the concept of Fermi-Dirac statistics of these electrons. Then I would like to see how different properties change as you increase the temperature. How does the heat capacity depend upon temperature? How does magnetism depend upon temperature? And I'll try to squeeze some time to describe the concept of Landau quantization, which has this two-dimensional electron gas or C exposed to a magnetic field. The energy levels get quantized further because of the magnetic field. And this concept of Landau quantization is at the heart of almost 70 to 80% of modern condensed matter physics. So these are really fundamental concepts, basic concepts. I've tried to simplify these concepts as much as I could to you, because if you understand these concepts which have been diluted to you without compromising the rigor in a simple fashion, in an understandable, comprehensible fashion, you can go a long, long way in condensed matter physics research. So this is all that I wanted to say for today. The next lecture is probably going to be our last lecture on quantized free electrons, and then we're going to shift to the band theory. Any questions?
सर व्हेन इज आवर मिड टर्म, उसकी डेट आपने अनाउंस नहीं की है अभी.
Well, when is the midterm week? Do we specified the midterm week?
नो सर, यूनिवर्सिटी ने आई गेस स्पेसिफाई नहीं किया, और ये क्योंकि सेमेस्टर ऑनलाइन ही चल रहा है तो अ लॉट ऑफ कोर्सेज डोंट एक्चुअली हैव मिड्स, डिफरेंट तरह के प्रोजेक्ट्स हो रहे हैं, तो इट्स अप टू यू कि आप जब भी देना चाहें.
लेकिन आई गेस सर नेक्स्ट वीक से स्टार्ट हो जाएंगे मिड टर्म्स वैसे जनरली.
This is the 11th lecture. I have to do a makeup. So I think after the 13th or the 14th lecture, I'll probably the week after the next week.
ठीक है सर, थर्ड वीक
and I'll give 6-7 hours to attempt the midterm exam, and
ठीक है,
I'll
तो
follow
सर
the
फिर
honor
उसको
code. Yes.
सर ओवर द वीकेंड रख लें फिर, अगर तब तक हमारे लेक्चर ही पूरे हो जाएंगे तो इट विल बी आई थिंक 13th और 14th ऑफ मार्च।
नहीं, मैं एक दिन दूंगा, वीकेंड पे मैं कोई एग्जाम नहीं लूंगा ना।
सर दिन जो देंगे वो फिर आप उसमें क्या कहते हैं,
मंडे वेडनेसडे
वीकेंड पे यानी सैटरडे संडे में से कोई नहीं कर सकते या वीकडेज में से ही करेंगे?
सैटरडे संडे मैं एज अ मैटर ऑफ प्रिंसिपल नहीं करूंगा।
ठीक है, और सर मंडे और वेडनेसडे के अलावा फिर चल जाता है किसी भी दिन।
चलें देख लेंगे वो।
और सर
ऑलराइट जी।
सेकंड सर एक चीज मैं रिक्वेस्ट करनी थी कि सर इज इट पॉसिबल कि नेक्स्ट वीक हमारा होमवर्क कोई ना हो, क्योंकि सर 4 होमवर्क्स तो हो गए हैं और मतलब वी फील ओवरबर्डन इन सम
how do we
वेज।
cover this material? Because this material is really important for the midterm, but this is fundamental material. So I was actually planning to send out the 5th homework today. That will help you in the midterm as well, because this is really fundamental and important material.
तो सर उससे अगले वीक में आप मतलब क्योंकि हमारा बहुत ज्यादा हर कोर्स का ही नियरली हर वीक होमवर्क आ रहा है, तो नियरली हर वीक हम 4-5 होमवर्क्स कर रहे होते हैं, तो इस वजह से कह रहे थे कि कोई एक वीक हमें अगर फ्री मिल जाता।
चलें देखते हैं, इंशाल्लाह देखते हैं।
ऑलराइट, थैंक यू।
ओके जी, शुक्रिया, खुदा हाफिज।